Good morning. As I always say, I hate to interrupt good conversation, but in this case I have to. In fact, in all cases I have to. Isn't it good to be back? Yes. Julie was just telling me a couple of minutes ago, 26th of February 2020 was the last time we had Coffee and Friends. So it's been way too long. And it's great to see you all here. In fact, I don't know whether we would have fitted into Wesley with the numbers. It's good to see lots of faces that we've seen before, and also some that we haven't seen before. So if you are new, well, Coffee and Friends, welcome. Hope you have a good coffee and a good conversation, and we're about to hear a great speaker. So that brings us to the main event for today, and Tim has a most impressive CV. He's got a PhD in biochemistry from Monash University, and during his career he's been a senior tutor at the University of Melbourne and a senior research officer at Royal Melbourne Hospital and St Vincent's in Melbourne. I've praised this down, Tim, from what you sent me. This is the what do they call it? The executive summary. He's been a lecturer at Deakin University and the University of Wollongong, and a visiting research scientist at the Rockefeller University in the USA. He's a postdoctoral fellow at the Alfred Hospital in Melbourne. He was an adjunct professor at Deakin University and a lecturer at Oxford University. He's conducted research in 4 different fields of medicine related to glucose, insulin, cholesterol, and interestingly, drought and salt tolerance in croplands. Tim's major interest is ornithology, that's birds I think, yeah, the ones that, and his hobby is photography. We came to know Tim through his membership of the Berry Apple Users Group, and he's become a friend. And it's great to have you here today, Tim.
Thanks very much.
So let's welcome Tim. Oh, and one more thing before I go. Next month, our speaker is our very own David Foley. So that'll be talking about Opera Australia and various things music.
Journey, yes.
Okay, well thank you, John. It's a pleasure to talk to you. Some of you will have heard part of this talk before. I gave the exact talk on last Monday night at for Probus in Journal. And so let's get started. I couldn't help but use my picture of a Gerringong sunrise. Okay, so my talk is going to be about trying to demystify a lot of the stuff that's going around in the press and politicians. So it's all about the vaccines that are being developed. And the first thing I want to do is a bit of a cautionary tale in that the press and politicians talk about COVID as though COVID is the virus. COVID is not the virus. COVID is the disease that's caused by the virus, hence the D. The virus's name is SARS-CoV-2. So that's self-evident. If there's a SARS-CoV-2, then there must have been a SARS-CoV-1. Sure enough, there was, and it was discovered, if you like, in China. Where else? It was 1/10 as infectious as our present COVID. It didn't travel in aerosols. and there was an epidemic but not a pandemic, and it only lasted for about a year. So there's the beast. Now, you will have seen on the television that sort of thing, but they never show you what's inside it. They just have a ball with spike proteins around the edge. Now, what's inside it is the, if you like, the intelligent part of the virus. It's the messenger RNA, ribonucleic acid, which codes for all the proteins that make up that virus. Okay, the overall scheme, because very few of you are biochemists, so you might not know how the whole scheme works. DNA, which you've all heard of, can be translated or transcribed, into ribonucleic acid, which is RNA, and that can code for proteins. And that's how it all works in all of your bodies. So let's think about what happens before vaccines were available. Well, SARS-CoV-2 enters your body. It immediately goes down your windpipe. It finds the soft tissues of your lungs and begins to infect those cells. Once it's found a suitable place to bind to, it then cuts its way through the membrane of your cell and injects its messenger RNA. So then what happens next? Well, the messenger RNA enslaves the protein-making ability of your cell. And that's what we would call an infection. So that message is translated into virus proteins, and your own cell assembles new virus because it's been enslaved by the virus. So your cell actually gets totally enslaved and makes new virus, which it releases. It goes further into your system, it goes into the blood, and then starts reinfecting in multiple cycles. So we might ask ourselves, how do we develop immunity? In general, how do we develop immunity? The answer is that your body's immune system learns to recognize foreign proteins, which we call antigens. So pathogenic proteins, which we've inactivated, can be then safely injected into your arm muscle. And those antigens are, in fact, the vaccine. So the antigens can enter your bloodstream, and they do that slowly. Otherwise, you would get an anaphylactic shock, and you'd all have to have an injection of adrenaline. So that's why your doctor or your nurse will say, please wait for 15 minutes to make sure you don't get a bad reaction. So those antigens, once they've got into your system, cause the production of antibodies in a very complicated series of reactions which happen in the blood. So what do all antibodies look like? Well, they're all Y-shaped proteins, and they've got a business end at the end of the arms of the Y where different antigens will bind. And each of those binding sites is specific for the antigen in question. So let's think about those spikes. You've all heard that there are different variants being discovered, genetic variants, and each of those produces a new type of spike. Therefore, it produces a new type of antibody. So the list of antigens that we know about, of course, you will have heard them all. The normal, which we've sort of got, the UK variant, the South African variant, the Brazilian variant, and the most recent is the Indian double variant. In other words, it's got 2 genetic alterations. So now we've got some different antigens that the antibody has to play with, and they will bind to different areas on the arms of the Y-shaped protein. So we might ask ourselves, well, what do antibodies do? Well, they can circulate in the blood for months or years. You will know that if you have a tetanus injection, that's a vaccine, but you then have to have a booster in, say, 5 years' time, because the antibodies it produced will have been used up. So, they circulate for a while, they recognise new invading antigens. Those antibodies then lock on to the antigen, and an antigen-antibody complex is formed. So that green bit is the antigen. It can be any antigen of interest, and it's now bound to the antibody. The antigen-antibody complex is very large, and the bloodstream doesn't like large things floating about in it. So enzymes begin to chew away the complex. So the net result is that that naughty invading antigen is eliminated. So for all intents and purposes, as they say, the disease is cured. So here we have a nice picture of antibodies attacking spikes. So you see there are lots and lots of antibodies in the pinky coloured thing attacking the spikes on the virus. And they will, in fact, activate the virus because it won't be able to bind to your cells. Okay, let's look at some examples of antigens or pathogens. Of course, you've got SARS-CoV-2, you've got polio, you've got measles, you've got adenovirus, which is the common cold one, and you've got boring old influenza virus. So you need to recall that any pathogenic protein is an antigen and will cause the production of antibodies. So, what type of vaccines can we make? And this is the guts of the talk. You can use the whole virus to make an antibody, or you can put the messenger RNA inside another harmless virus and inject that, or you can rely solely on the actual nucleic acid. In other words, you can start with a messenger RNA. So let's gradually go through these different types of vaccines. The whole inactivated virus is used, and this is being done in France. It has been successful in primates, in other words, monkeys. And so all of the virus's proteins will elicit antibody production. So you get the feeling perhaps that your system will be able to cope with all future variants because it's making antibodies to the whole virus, all the proteins in the virus, not just the spike. So those are our newsworthy vials, which you've all heard about, though you never actually see those looking things. Okay, so that's whole virus vaccines. Now we'll go on to viral vector vaccines, and by that I mean that you put the messenger RNA inside a harmless virus like adenovirus, and then you inject that. So here we have just a drawing of the DNA on the left and the RNA inside a virus. The adenovirus is, I'll show you the shape of it on the next couple of slides. And there it is. It's I don't know, I don't know what sort of geometrical figure that is, but it's something like an octagon. Anyway, it's containing the message. It's hard to see the message on the one on the left, but I've got an arrow showing the spike mRNA inside the harmless virus, and that's right next to your lung cell, ready to do its work. Okay, the carrier virus, which is the adenovirus, injects the spike mRNA into your cell. And what happens when you have mRNA going into a cell? You won't remember, but it takes over the protein-making machinery of that cell. Now, the viral vector vaccines are the ones that are being made by AstraZeneca. The CSL, Commonwealth Serum Labs in Melbourne, is making the thing, and under licence from Oxford, and it is approaching 1 million doses per week. But the TGA has to test every batch, so that is why there is this enormous delay. Okay, it costs $5 per dose, which Scotty in marketing was paying for, and it can be stored at 2 to 8 degrees, in other words, normal fridge temperature. That's good. So let's go on to the third type of vaccine, which are nucleic acid vaccines. Here, we put the RNA inside a particle, we coat it with harmless fat, and it is the fat droplets that are then injected into your arm. Your muscle gradually strips away the fat, and what are you left with? Messenger RNA. And that goes through the same process. It makes antibodies, and that's how the Pfizer and Moderna vaccine works. So spike proteins very rapidly appear in your bloodstream, and they cause the production of antibodies. The cost is $25 per dose, not $5. It's imported from the US and Germany, and the whole manufacturing process takes 60 days minimum. So let's look at what we might call the take-home message. Spike proteins are inactivated and the virus can't get into your cell. So both of those, the last two viruses that I've talked about, produce antibodies which inactivate the spikes. So vaccines will prevent SARS-CoV-2 from getting into your cell, because unless the spikes are interacted with, it won't be able to cut a hole in the membrane to let itself in. So, in great relief perhaps for some of you, my time has run down. And because I'm an ornithologist, it's now your turn to ask questions. Right, go ahead. I've got a couple more slides, particularly about after effects. So, if anybody wants to know about that. Yes?
Well, firstly, thank you for simplifying a very complex subject. My question is, we're hearing that there is an increasing percentage within Australia who are deciding not to vaccinate at all. Can you run through what you think that will do in terms of long-term herd immunity in the society?
Yeah.
But also, where do you think pandemics of this type are also heading? Are we going to see more of this?
I think we probably will see more of it. The question about people refusing to have the vaccine, I think they're believing in a conspiracy theory.
Yes.
Which is very dangerous. And to get herd immunity, as far as I know, you need at least 80% of a given population to be producing antibodies. Yes.
I was interested in the efficacy between the two vaccines that are available in Australia, because the Pfizer
and Astra.
Yes.
Yeah. Oh, I think basically isn't that much difference in the efficacy. They say that after the second injection with the Pfizer, it brings it up to something approaching 80 or 90% effective, whereas with the second injection of the AstraZeneca, it brings it up to about 70 or 80%. So, yes?
In the media, they say that it doesn't prevent you getting an infection, it might just lessen the symptoms when you do catch it.
Yeah.
So does the vaccine actually eliminate the infection, or does it just lessen the symptoms?
I'm not sure I can hear you completely.
Just go to the microphone.
Can you hear me now? Okay.
Yeah, I think what you're saying is good, but it's very muffled, and maybe I'll sort of...
Oh. So I was just wondering, me would say that it doesn't create, in other words, you still get the infection if you get vaccinated, it just lessens the symptoms. So is that correct? Is that correct, that it only just lessens the symptoms, but you can still actually...
Yes, I'm not sure.
Like right at the beginning you said virus, disease.
Yeah.
Okay?
Yeah.
So the vaccine is to attack the disease.
That's right.
So you will still catch the virus,
Oh yes,
and the vaccine will stop that virus causing the disease in your body. Is that,
That's
could
exactly
you explain that a bit? I think
Exactly.
that's kind of the question, something along those lines.
the reason that it is effective is that it's an antibody against the spikes. So if you imagine spikes sticking out of that thing and an antibody comes and binds to them, they literally physically can't bind to your cell there and they can't cut a hole in it. So I don't know quite what the answer is to your symptomless infection. I think some people's bodies will be able to fight it off straight away, like little kids under 16 sort of thing will be able to fight the virus off because their immune systems are highly charged. They've all probably had their mothers have sent them out into the street as soon as she found out that there was a chickenpox child in the street. So their immune systems are highly, their machinery is working well. So it could be that people who don't have any symptoms, even though they might be a bit older, their immune system must be working well.
Thank you.
Yes.
There seems to be some confusion as to whether we should take the AstraZeneca or the Pfizer vaccine. The Pfizer vaccine is not available right now because of the delay, nor is the AstraZeneca one because of the protracted delay with the TGA having to approve it. Why does the TGA have to approve every batch? Surely this is jobs for the boys. If the thing is approved and it has an ISO standard, why does the TGA have to re-approve it?
Yeah, a good question, but the fact that every 300 litre vat of this stuff that's being made, there can be little mistakes because it is a biological system. And the TGA wants to ensure that, 10 samples out of this 300 litres are going to be effective. In other words, can they detect antibodies in an in vitro system? Yeah. If they can, then they know it'll be okay.
It's not so much they're approving it, they're testing it, is that?
Oh yes, they're testing it and therefore saying, we approve this for injection because it doesn't cause anything worse than it's meant to cause.
No.
Okay. Maria?
Tim, once we've had our first injection, which a lot of us have, we've had our first injection, are we then safe from catching the virus?
You are safe, but your system will have just sort of got onto its legs a bit and it'll be producing antibodies, okay? But the reason you then need a second injection is to make sure that everything is in full working order. Yeah. But don't be scared, the first injection will give you protection, but it won't be as long lasting as after you've had the second. John?
Are we going to need another one after 12 months, like a booster?
I have a feeling we will, and there's just a little thought that maybe the antibodies that you do produce naturally against this virus won't last. So you will need a booster.
And they're saying now that it's not a bad idea to actually mix and match. So if you had AstraZeneca to start off with, you might have Pfizer in 12 months' time.
Yeah, in fact, it's just discovered 2 weeks ago, been reported, that if you have one of each, you get much better protection than the same one again in 12 weeks. And another point just that has come out in the last week is a group in, I think, Queensland, has produced a drug, I don't know, I think I know roughly how it works, which you take and that changes the receptors on your cells, so the virus then can't attach. So that's another way of doing it. You either try and kill off the virus, or you change the architecture of the cells so that the virus won't be able to bind.
And can each new variant of the vaccine deal with each new variant of the?
So far, even the Indian variant with its 2 mutations is still going to be defeated by the Pfizer, at least. Andrew?
I'm just listening to some language. So if you, just say you've been vaccinated,
Yep.
you can still catch the virus.
Yes. It's still in the air.
Yeah, yes, but its impact on you is dealt with by the vaccine. Yes.
Exactly.
But of course, if there's 80% or more vaccinated, then there's less spreading and less going from person to person to person.
Exactly. And in fact, interesting figures came out from the US about the compulsory wearing of masks. Last year, in, well, let's say somewhere in the 2020, they had something like 27,000 cases of the flu in the American population for that year. But ever since we've been wearing masks, it has come down to 6,000. So masks are doing a second service. They may be preventing you from getting the aerosol from the SARS, but they are also effective because there's less breathing in each other's faces for the normal flu. Yeah.
How were labs able to predict the fact that we were going to get a virus before it appeared? They, we're told that they had been working on it because they knew this was going to happen.
I don't think so. I don't think they knew. I think what happened was a good lab, like a lot of them, molecular biological labs down in Melbourne, have all the equipment and they know what viruses will do. So I don't think there was such as a prediction but the fact that they had all the equipment and ready to fight the pandemic. Anybody else?
We're being told that the international borders probably won't open until 2024.
Is that so? 2024?
That was the latest.
Well, I hope they open a little bit earlier.
For international travel. What do you think will happen when the borders are open? Will we see a pattern of increased infection?
We will, we will see a pattern of increasing infection, say, if we allow too many people who've been through Delhi to get into Australia. But there are green areas and there are red areas in the world. And so long as Australia only lets the green area people, then the chances are much less.
There was a question here before about the likelihood of more pandemics in the future. What do you think about that?
I don't know that I could predict that. But I think SARS-CoV-2 has shown that it's a very dangerous infective virus, and it just gives you the potential feeling that there must be other viruses about that could so easily take on the same properties. So I think the chances of another pandemic are much higher.
Reactions to the having the injection, we seem to be poo-hooing the fact that it does happen, and everyone gets it at a certain stage.
Yeah.
And the women don't seem to get it as much as the men.
Yeah, I'm not sure about the
Well, I thought that they have a better immunity.
I don't think so.
You don't? Well, it was written in the paper. Can I just say, I think it was the second slide you put up on dates. I queried the date that you said that it happened. You were saying late 2020.
No.
Didn't it happen before that?
No.
The second slide you put up.
Yes, I know. I may have said it, but you could read that it was 2002.
2002?
Yeah.
I beg your pardon.
That's all right. I may have said it incorrectly. But it only lasted a year. And it was only an epidemic, not a pandemic.
Yeah.
So here, some people might be worried about the after effects of the virus. Or sorry, not of the virus, but of the vaccine. And there's a good little slide showing you for Pfizer what you can expect after your second dose. Now, AstraZeneca may have produced such a similar thing, but I haven't been able to find it. So you'll see that without exception, all the severity of the reactions are worse after the second injection. So if you felt off for about a day after the first injection, you might feel off for say 2 days. Yeah, sorry.
In addition to those side effects, there are also a number of serious adverse reactions that have been reported. Things like blood clots, stroke, heart failure, cardiac arrest, myocarditis, thrombocytopenia, neurodegenerative diseases, things like that.
Yeah.
Would you like to discuss the more serious adverse effects and the long-term effects?
I'm not sure that anybody has actually proven that, say, the AstraZeneca and clotting are connected. Because remember, as soon as that vaccine gets into your arm, there is an enormous dilution factor by the time it gets into your blood. So if there were any specific effects when it was concentrated, like to produce clots, which there's no scientific proof that AstraZeneca produces clots. What I would like to try and instill in all of you is a healthy disrespect for the press and for politicians. The only person you can listen to with any confidence is Norman Swan, because he keeps himself ahead of the literature.
Sorry. In America, there are nearly 200,000 adverse events reported in their VAERS system.
Again,
Some of which are very serious.
I want to see direct connection and proof of these things.
Well, surely temporal association is where it begins.
Well, again, I'd like it to be proven. Thank you for saying that, but I think that's unnecessarily scaring people. And another thing I can scare you with, if you want to be scared, is that the AstraZeneca, that adenovirus that it relies on, guess where it's coming from? Chimpanzees. But the adenovirus has been inactivated by reacting it with formaldehyde. So it's not going to have any of the nasty antigenic properties. Yes?
Isn't it fair to say that there are some people who will get that thrombotic problem regardless? You know, I know I was a GP years ago and I saw someone with exactly the same thrombocytopenic reaction of clots because of a drug I prescribed. Now, there may be some in this room who may have a propensity for clots, and that one person may get it, the rest of us may not. You either have that propensity or you don't. Is that what you think or not? That's my feeling about it. That if you're going to get it, you're going to get it. If you're not going to get it, you're not going to get it.
That's right. In fact, we talk of the general thing, we call it comorbidity. So if you've already got a propensity for heart attacks or clotting, then maybe you should rethink your wish to get the vaccine. In fact, in the talk that I gave to Probus, there were two people in the audience who were on blood thinners against just to produce no clots. So
I'm on blood thinners.
I bet there are several in this room who are.
yes, no doubt, no doubt.
I think just a comment, if you take the worldwide number of people that have been vaccinated, compared to these numbers that we're talking about, it's minuscule.
It's
the
minuscule.
people that have problems. And therefore, go and get the vaccine.
Yeah, the clotting thing is, what is it, 1-2 cases in a million?
Absolutely. You know, and therefore there are other vaccines that we're probably taking for other complaints, which are far more serious, likely to provide more serious effects than this.
Absolutely.
So far, please go and get it.
Please get vaccinated.
Are there any chances of any more variants?
Are you worried that there will be more?
I'm asking, is there a chance there could be more?
Well,
What have we got 4 now?
Yeah, of course there's going to be more, because the DNA and the mRNA system of the virus adapts to new situations, like an evolutionary process. So even though the virus has no intelligence, its chemicals can still mutate, just as the natural course of DNA. Some of you will know about DNA replication, where you rely on a certain truthfulness between one DNA and the next. It could be that 1 or 2 letters in the DNA will be different just by random biological function, and this will produce a different message, and that will produce a different protein, and we then look at it and we say, a new mutant. And just, it's unfortunate that the Indian mutant happens to have 2 of these changes in it, and yet the literature is saying that the Pfizer and the AstraZeneca are both equally able to fight off the Indian variant.
Could a variant be produced that would require a different vaccine or a...
Oh, it could, yeah, but I'm not here to speculate.
No, it's all... Yeah. We'd be lucky to be able to
Isn't this why the flu vaccine is constantly changing because of mutants, and we have to,
That's
they have
right.
to produce every year a different
but
vaccine?
you're right, the flu vaccine, normal flu vaccine, has one spot in it which keeps mutating. And from the Hong Kong flu onwards, we can predict what it's going to do, and so that's why you have to have a new flu shot every year, because that's being made against the new virus, the new mutation. Because remember, the flu is also a coronavirus. Rob?
In the viruses and bacteria can mutate.
Yeah.
They can become more virulent and more infectious, or they can become less virulent and less infectious.
Yes.
Remember scarlet fever? That killed millions years ago, but it became less virulent and less dangerous about 80 or 90 years ago.
That's right.
Now, we don't know which way this is going, do we?
No, we don't.
We hope to goodness it gets less infectious.
Yep.
In fact, it does better then because it doesn't kill so many people off. The virus would do well to become less infectious and less virulent, not killing off the host, and then it can keep going. If it kills us all off, it won't survive.
True. But that's asking a lot of the virus. Intelligence.
On that hopeful note.
Anyway, thank you all for listening and asking questions.
On that hopeful note, Rob, so let's say thank you very much for Tim for coming to speak to us today. And I know that there's so much involved in all the knowledge and all the bits that are coming out in the press, and I think that's probably helped to get things a little bit clearer in our minds. And but I think the bottom line is get your jab. Thanks everybody for coming. It's been wonderful. Please stay and talk and have more coffee and tea. And thank you so much, Tim. Can we just give him another round?